It's time to start. Today, I²CNER seminar. Today, the speaker of I²CNER seminar is Professor Koichi Okamoto, Department of Physics and Electronics, Osaka Metropolitan University. First, from Matsumoto sensei.
Okay. Thank you, Kina, and hello, everybody. My name is Hiroshige Matsumoto, and I would like to say a few words at the beginning of this seminar as an associate director. And I'd like to explain about this seminar series first. Since the establishment of I²CNER in 2010, this seminar series has hosted internationally recognized researchers working on a wide range of topics related to carbon neutral energy. And the seminar provides a platform to share cutting edge research and to encourage interaction among researchers and students. Today, we are pleased to welcome Professor Koichi Okamoto from Osaka Metropolitan University. And the title of his talk is Metaphotonics for Generation Optical Devices. And honestly, I'm not so familiar with this topic, but I'm looking forward to learning something new from this so exciting topic. And I hope you will enjoy the seminar as well. Thank you.
Thank you. Thank you very much.
Thank you, Professor Matsumoto. So, if you, Professor Okamoto, prepare slides. Oh, okay, so
Okay.
I can see. So please start if you're ready.
Yeah, thank you very much. Thank you very much for the very kind introduction. I'm Koichi Okamoto. I'm in Osaka Metropolitan University. So today I'm going to talk about metaphotonics for the next generation optical devices from the Plasmonics and the Metamaterials to strong light matter interaction. So that's Osaka Metropolitan University was established 2022 by merging the two public universities in Osaka, Osaka City University and Osaka Prefecture University, and we became a very large university. And for the student number, the third largest national and public university in Japan. So first one is the University of Osaka, and the second one is the University of Tokyo, and the third one is our university, and the fourth one is Kyoto University. So please remember this university. So okay, I'll start. And this is my biography, and I got the PhD from the Kyoto University, and yeah, that's my experience. And from 2001 and 2007, I was in the California Institute of Technology in the United States, and at that time I started my research about nanophotonics and also plasmonics and metamaterial. Okay. And that's my acknowledgement. And my research group is Quantum and Optical Devices Engineering Group. And that's this year's group members. And that's a research collaborator and research founding. And now we have two doctoral course students, and next year also two master course students promote to the doctoral course. That's very important for us. So then, okay, next I'll explain what is quantum and optical device engineering. What is our final goal? So that's slide is for the quantum and optical device engineering. And nowadays, the electronics device is very important, and especially based on the semiconductor technologies. And it has been very developed, but almost to their limits, especially for the downsizing and the high integrated circuit. But much more higher speed operation and higher density integration and higher variety and functionality is required. And people using the EUV lithography, it's very expensive equipment, almost $300 billion, and to make the 2 nanometer anode structure. But it's very tough work, and it's almost reached the limit. And at the same time, also the quantum devices are well expected because that performance is very, very high. But in many cases, if you're using the superconductivity, so therefore the quite low temperature is necessary. So almost zero temperature is necessary. That's why the equipment will become very large and also very expensive. Then another method is using the optical and the photonic devices. And using the one big merit is using the optical photonic devices, we can achieve the quantum devices at almost at room temperature. That's a very big advantage. But we use the laser beam for the light source. But to controlling the laser beam is a little difficult because using the mirror and lens, mechanical controlling is very unstable, and also the very wide area is necessary like that. That's very also tough fact. That's a very important thing is that to confine the light inside the nano circuit. If we can achieve that, it's very convenient. And also we can fabricate the wearable quantum computer like such kind of the iPhone or Apple Watch or something like that. So we call that smart photonic devices. And to realize that, very important thing is how to confine the photon inside the nanospace. And to the light and matter resonance is very important, and very small volume and high quality factor is very important. And very important key technology is, of course, nanotechnology. That one is for 6 years, I was in the California Institute of Technology, Caltech, nanofabrication group, because for that time, that research group is the lead for the research field of the nanotechnology. Then I joined that research group, and all these structure we fabricate in that research group, and also we try to confine the light inside such kind of the nano structure. And the very important thing is, as I said, compared to the electronic technologies, the photonic technologies offer very high speed and greater functionality, and also the lower energy consumption, and also the very clean operation. And also, most important thing is the quantum devices operating at the room temperature are feasible. But the problem is, however, the manipulation of light into the nanoscale remains a challenge because wavelengths of the light is almost several hundred nanometer. So it is difficult to confine the light smaller than the wavelengths. So the key technology is nanophotonics, and also the plasmonics and the plasmic metamaterial. And nanophotonics is, as the name suggested, we fabricate the nanostructure and try to confine the light, and we try to control the optical property and the optical function. Like that. For example, by using the photonic crystal nanolaser, we can confine the very strong light at the center part, and also we can control the emission efficiency. And also plasmonics is we can confine the light between the interface between the metal and the direct material. Then we can strongly confine the light, and we can use that. And also we can control the optical property and the function. And based on that nanostructure, the material is called the plasmonic metamaterial. Then, so when I was joined to the Celtic group, so he was my boss, Axel Scherer. He was the first person to succeed making the photonic crystal nanolaser. And that person is a very famous Professor Eli Abronovich. So Eli was at that time a visiting professor, came from the UC, that time was UCLA, and now he is in the UC Berkeley. And he's inventor of the photonic crystal, and he's candidate of the Nobel Prize. And this is a good opportunity for me. Then I asked to him that I want to run the photonic crystal to enhance the optical property of the light emitting material or something like that. Then that time he's answered, you have to run the cytoplasmal resonance. So, but that time I couldn't understand that. And my impression, cytoplasmal resonance is very fundamental physics and not related to the device application. But now many people using the plasmonics for the device application. That's why I thought he is very smart. Yeah, smart guy. And also, first 3 years I was in the electrical engineering, and another 3 years I moved to the department of the physics, and I working with Harry Atwater, and also I working for the Axel Scheller and also the Harry Atwater, and he named the Plasmonics. So he's one of the pioneer of the Plasmonics. And we can control the numeric color or some property using the surface plasmon resonance. And he asked me when he named the Plasmonics, he asked me how do you think about the name of the Plasmonics? And that time I answered, I think that's strange. So Plasmonics is some strange. And for my first paper, I said, I don't like to use the name of the Plasmonics, and I just use the surface plasmon resonance. But now the name of the Plasmonics become very famous, and also that's very important for the priority. That's why I think that's very important. That's why it's for the so some you in the near future you found a very good for the student. If you in the future you found a very good thing, good foundation, please name the very bold name or very tricky name. That's very important for the priority. Okay. Then first time I ran the photonic crystal and I fabricate the structure, and we can confine the light at this part, and we obtain the laser oscillation, that's nano laser. And also by using the optical near field microscope, we observed the first successful image of the optical mode confined in the nano laser. That's the first time in the world. Then we measure the smallest mode volume, and that's threshold also lowest threshold at that time, and also that means the smallest mode volume 0.03 micrometer cubic. That was the smallest one. And that's why our result was introduced by the textbook, and the quality factor is 10 to the 4 power, and also the mode volume is 0.03 micrometers cubic. Okay, then by using the similar way, we fabricate by the etching technology, we fabricate the nanopillar array structure for the indium gallium nitride light emitting semiconductor material. And then important thing is these two pictures, the same condition. You can see the nano-fabricated region is very bright. So, and also important thing is that you can control the light intensity and also the spectrum and also the emission lifetime. With decreasing the structure, the lifetime becomes shorter and shorter. So that's important thing that you can control the spontaneous emission rate. And also another important thing is that you can see that's moving. You can see the blinking feature. Right? That we found we fabricate the nanostructure, the two-dimensional quantum structure has a blinking like a single quantum dot. But that size is several hundred nanometer. It's much larger than the quantum dot, but still it's a similar features obtained. And for that time, we couldn't understand what happened, but recently we found that this blinking is not a random blinking. Some patterns correlated, so that's synchronized. That's why it should have some quantum entanglement state or something like that, and it should be useful for some quantum devices. So, and recently we published this paper again, and for the correlation, and that picture was the cover of the Journal of the Applied Physics Letters. Okay. But for this structure, so to fabricate such a structure using the E-beam lithography, it takes a very long time and very expensive. For example, so to fabricate a structure for the one warehouse, maybe more than one night is necessary. That's why more easier way is important. Then we try to use the surface plasmon resonance, as Professor Abramovich suggested. Then some of you may familiar or not familiar with the surface plasmon resonance. That's a combination technology of the photonics and electronics that we can couple to the light and electron at the metal interface. Then we can obtain the both advantage of the photonics and the electronics. And yeah, that at the metal surface, it has some special plasma oscillation of the free electron. It's a surface plasmon mode. And the surface plasmon is plasma oscillation. That's why it cannot couple to the light directly. But if the surface plasma is generated, the partial charge was distributed, and it's a polariton. It's some kind of the electromagnetic wave. Then that surface plasma polariton can interact to the light. Then we can couple to the light to the electron. So if you shine the light at the interface, usually it's deflect or diffraction, but just light was confined at the interface. Then you can obtain the giant electric field enhancement at the metal interface. Sometimes it's a million times larger, something like that. And it's enhanced light absorption and emission and scattering near the interface. Then it should be useful for the ultra-sensitive sensors, like a SPR sensor or surface enhanced Raman spectroscopy. That's one advantage. The other advantage is the light can be treated as a nanoscale because it's strongly confined, coupled with the electron. That's why it's much better. You can treat the light smaller than the wavelengths. Then you can use that for the optical nanotechnology and the nano-optical waveguide or optical nanocircuit. So yeah, that's very important to merit. And if the surface plasma is generated at the metal interface, it's a propagation mode, two-dimensional propagation mode. And if the surface plasma was generated at the metal nanoparticle, in that case, that's a localized surface plasma mode. So surface plasma has these two modes. Then, so there's several application methods, but I think that the surface plasma is the coupling of the electron and photon becomes strong. That's why I think that the energy conversion of the electron and the photon must be increased. Then we try to use that to improve the emission efficiency of the light emitting material. Then we succeeded. So we published that in the 2004 in the Nature Material. And recently, many people know that the surface plasma resonance is useful for the light enhancement and high emission efficiency. But that was the first experimental result. And that method is very easy. We prepared a single quantum wave of the indium gallium nitride light emitter and just deposit a metal film at the top of the wafer. The thickness is 50 nanometer. That's it. Then we excite the quantum wave from the backside because that metal is very thick. So we excite the quantum wave from the backside and we detect the. Okay. Then we obtain the light emission from the backside. Then we can obtain the more than 10 times enhancement using the silver and also some enhancement with the aluminum and no enhancement using the gold. So, okay. Then and we also find that that's not only for the intensity, but also it's enhanced the small cell emission rate. Lifetime becomes very short. That's very important thing. And the interface of the silver and the gallium nitrides, the surface plasma is generated at the blue light region. That's why that enhancement is very large. But for the aluminum interface, the surface plasma resonance is generated at the UV light region. That's why it becomes small. And for the gold interface, the surface plasma is generated at the red light region, and there are no mode at the blue light region. That's why for the gold surface, there are no enhancement. So we found that surface plasma resonance is useful for the high efficient light emission. And that's why I published, I was said so, but there are no nanostructure. How the surface plasma can couple to the light, I was said. And usually surface plasma coupling needs such kind of the periodic grating and diffraction grating structure. But the good thing is for the metal evaporation, it's some random nanograin structure. So that grain size is almost similar to the wavelength of the surface plasma polariton. That's why the direction is become very broad, but very easily surface plasma can couple to the light. Then that's a mechanism. Then the mechanism of the enhancement of the spontaneous emission is a partial effect. partial effect was published at 1946. That's a very old paper, and that paper is just a half page, a very small paper, but that's a very important effect. If you put the light emitter inside the cavity, if so, the coupling of the light emitter and the cavity, the spontaneous emission rate was enhanced, and emission lifetime becomes shorter. Then that enhancement factor should be proportional to the quality factor of the cavity and also the mode volume. Then Eli Abramovich suggested that also surface plasma coupling is almost also similar to the such kind of the resonator. So that enhancement is also he predicted that the surface plasma coupling should enhance the spontaneous emission rate. Then experimentally we show that. Then spontaneous emission rate is due to the non-radiative recombination rate and the radiative recombination rate, and then partial enhancement factor is proportional to the density of state by the Fermi's golden rule. And then that's partial enhancement factor is obtained by the experimental time-lapse experiment, and also the density of state we can calculate by the dispersion diagram. Then this value is very close. That's why this result suggests our model. Then if so, internal quantum efficiency of the light emission is a rate of the radiative and the non-radiative recombination rate. Then partial effect should increase the radiative recombination. Then finally, let's increase the internal quantum efficiency. Then that's enhance the efficiency. And the good thing is for this region, this dotted line is the best coupling region. The best coupling region efficiency is almost 100%. So that's very important. And also Professor Abramovich suggested that based on this phenomenon, we can obtain the much faster emission rate. Spontaneous emission rate can be much faster than the simulated emission. So the important thing is that that's not a simulated emission, it's a spontaneous emission. But still, it's incoherent, but it can be much faster than the simulated emission. And then he's named that the spontaneous hyper emission. And he proposed that at the MRS 4 meeting in the 2013 in Boston, and that's a keynote speak. And that time I was a chair of his talk, and I so surprised that that was proposed. That's a very interesting phenomenon. Okay, then after I published the light enhancement at 2004, and I said easily we can develop the device application, but first device application is the 2070s. We take more than 10 years because the device structure is a little difficult because the light emitter must be very close to the metal surface. That's why that p-type layer thickness must be the 10 nanometer or 20 nanometer. That's very difficult to make the device structure and to keep the PN junction. But finally, we can fabricate the structure and we can obtain the more than 2 times enhancement, even for the electrical pumping. But for the photo pumping, we obtain the more than 10 times enhancement, but the electrical pumping just only the 2 times enhancement because the optimization of the device structure is not good enough. That's why further optimization is necessary, but at least we can show this method is also useful for the electrical pumping, and the device application should be available. Then 2017, we published the review paper. That's why if you are interested in the detail, please read this paper. And also the many another group try to improve the LED efficiency by using our method. And many group have many type of the metal nanostructure. But unfortunately, enhancement factor is up to 2 because still the electrical pumping is difficult. But theoretically, it must be available, and 100% efficiency should be available. And also, we wrote the book chapter of this, and if you're interested, please read this book. And also, that's a Japanese book, Active Plasmonics in the Corona shipment. So, yeah, if you're interested in that, please read that. Okay. And that's an enhancement. And the next important thing is how to tune and how to control the resonance condition and the resonance wavelengths. So that's very important. And as I said, there are two modes. One is propagation mode and another one is localized mode for the surface plasma. And the propagation mode is some kind of wave. That's why it has some dispersion diagram. That's why it's momentum and that's photon energy. And light can use only this inside the light line. But the surface plasma mode exists outside of the light line. That's why normally the coupling of the light and the surface plasma is difficult. That's why you have to make the nanostructure and the momentum matching is necessary. But using the aluminum, that peak portion is the deep UV light region, and the silver case that's blue, and the gold case is red. And to tune that peak was difficult. But you can control the momentum, and then matching condition was controllable. That's why momentum is tunable. That's why by using this method, so the almost 100% coupling condition is available. On the other hand, the metal nanoparticle case, in that case, by changing the size and shape of the metal nanoparticle, you can control the resonance peak. But there are no momentum. That's why you cannot control the matching condition. That's why easily you can control the wavelengths, but always it improves some energy loss, and the 100% coupling is difficult. So it has some advantage and disadvantage of these two modes. Then next, we succeed to enhance the blue light, and next we want to use that to enhance the green light, because the very high efficiency green LED is very difficult to fabricate, and this one is the commercial LEDs quantum efficiency, and the blue one is already very high, and the red one is high, but the green one is a bit low. That's why it's called the green gap problem, and we have to overcome the green gap problem. And also UV light also difficult. But someone say that the white light LED was combination of the blue light LED and the white light phosphor. That was, someone say that must be good enough. Even the blue light is very efficient. If so, that's okay, because white light LED is a blue and yellow combination. But using the yellow phosphor, so some energy loss was there. Then we want to make the RGB light source for the no loss white light LED, and also we want to use that for the micro display. In this case, the RGB emission, high efficient emission, is very important. Then next, we want to try to enhance the green light emission. But silver is good for the blue light, and the gold is good to the red light. That's why if we change the sample to the green light emission, with increasing the emission wavelengths, the enhancement factor becomes lower and lower. Then the green light region, the enhancement factor is almost 2 times or 3 times, something like that. Then we can control that by changing the size of the particle. Then we can control the resonance peak, but we cannot control the coupling condition. That's why that size is good match to the green light, but still the enhancement factor is only 4 times. That's still difficult. But recently we found a good way. If directly you put the silver nanoparticle directly on the gallium nitride, so the refractive index of the gallium nitride is very high, 2.5. That's why resonance peak become later shifted. That's one problem. And another problem is the 1 day or 2 days passed, the metal nanoparticle was destroyed. So metal nanoparticle is very unstable if it's on the gallium nitride. Then we put the silicon dioxide spacer sheet between the metal nanoparticle and the gallium nitride. If so, we can avoid the destroying of the metal nanoparticle, and also the refractive index of the silicon dioxide is very low, 1.5. That's why we can blue shift it to the resonance peak. Then using this structure, finally, we can obtain the more than 10 times the enhancement, even for the green light. So that's why if we can apply this for the device structure, we can overcome the green gap problem. But still problem is silicon dioxide is the insulator. How to make the electrical pumping is some problem. But still using such kind of structure, we can overcome the green gap problem. Okay. Then more flexible tuning is we want to use the metamaterials. So based on the nanophotonics and the plasmonics or something, so that's an artificial material based on the nanostructure. That's called the beta material. And John Pendley proposed and succeeded to fabricate that structure. And the first time he used this metal nanowire structure, and that's a split ring resonator structure. By combination of this structure, he can achieve the negative permittivity and the negative permeability. So if both value is negative, the refractive index become negative. So the minus reflective index is available. So then he succeeded that also experimentally by the microwave light region. Then many people try to increase the energy to the visible light region. If so, the structure must be smaller and smaller and smaller. That becomes difficult. And finally, let's reach to the 780 nanometer IR light region, but still it's difficult to achieve the visible light region. But that's one way. And also for the visible light region, recently, the negative reflective index is difficult, but people can control the light at the visible light region. So that's why recently the Plasmonics metamaterials mainly used not for the negative reflection, but just color controlling. Then anyway, you have to make the very fine structure by E-beam lithography like that. But in 2016, we fabricated the bottom-up process, just the metal nanoparticle, just put together the self-organization of the metal nanoparticle. Then we transfer that for the substrate. Then also, by the layer number, we can control the color. That's why such the very simple structure is also the metamaterial. So that's a random, that's almost periodic structure, but the random structure also useful for the metamaterial. So the important thing is how to obtain the very strong coupling of the light and the matter. So many people propose the many structure, for example, using nano gap or such kind of the multiple layer structure of the metal and the electric material, or plasmic nano antenna structure, or hybrid photonic and plasmic cavity. Or that one is the surface lattice, very aligned lattice structure. By using this alignment, people can enhance the resonance. But our new proposed method is that one, based on the very random structure, but the metal is there. That's why we call that metal hemisphere or mirror structure. That part is direct material. So metal nanoparticle and the electric spacer and the metal substrate. That structure is very good for the new type of the metamaterial with a random structure. Then we explain. Yeah, okay, I'll explain the structure. Then first, we calculate the FDTD simulation for the electromagnetic simulation. Then, if we put the silver hemisphere on the glass, in this case, just only one resonance peak is there. And that's why dipole mode, and the quadrupole mode is also there. That's only one color. Right? Then that's a simulation. And the experiment also, that's only one resonance peak, and also small quadrupole peak. But if we put this structure on the metal substrate and the spacer and the hemisphere, in this case, these two modes interact with each other, and it's some kind of strong coupling. Then the two modes couple each other, so it's a hybridize the two modes. Then that's because split it into the two modes. Then by controlling this size, we can control the splitting. And also, good thing is that peak becomes much more sharper and much more stronger. And that's a calculation. And then we can fabricate this structure by the deposition of the metal and sputter the direct material, and also the deposition of the very thin metal film, and also the thermal annealing. And so such kind of the random structure is very easily fabricated by the thermal annealing. So thin metal film was increase the temperature, it automatically it can form the random metal structure, but it's random and not aligned, and the hemisphere structure. But that's resonance peak is split into two and also very big and very sharp. So we can control the intensity and the sharpness of the resonance peak by using this structure. So we call that's the nanohemisphere or mirror structure, NIOM structure. Then, most important advantage of this method is you don't have to care about nanostructure. In many cases, you have to fabricate a very fine structure by the e-beam lithography. But in this structure, just a random particle is good enough. But you have to control this thickness. Then you can obtain the all RGB full color. That's the simulation and that's the experiment. And that's my sample color. And by just only this method, so 3 elemental color is also reproduced, and also the very sharp resonance peak and the quality factor 200 is also available. And controlling the thickness is very easy. Just controlling the evaporation time. Easily you can control the thickness. Then this structure must be useful for the full color light source or full color display. And we use this for the light enhancement also. And I used to cadmium selenide quantum dot and put on the gold layer. We obtained the 20 times enhancement, but very high efficient core shell structure, we couldn't obtain the enhancement because the emission peak is very sharp, but the plasmon resonance peak is very broad. It's not good matched. Then by controlling the structure, but 4-time enhancement is the maximum of the normal structure. But using this metal substrate and the metal nanoparticle structure, we can obtain the 14 times enhancement. That's why, because by using this method, resonance peak becomes very sharp and very good match to that's quantum dot peak. That's why you can obtain the huge enhancement using this method. And also next, we want to use this, we extend the UV light region because UV light is very important. And for example, aluminum gallium nitride quantum semiconductor structure is used for the deep UV light source and usually 260 nanometer region. And this wavelength is very important for the sterilization or lithography or optical memory, many things. But for this moment, there are no high efficient deep UV LEDs. Efficiency is very low. And as I said, aluminum has a electron density is very high and the plasma oscillation is very deep UV light region. That's why we just put the aluminum, we obtain the 7 times the enhancement of the 250 nanometer. And also, we want to extend more shorter wavelength region. Right? Then we fabricate that's kind of the NIOM structure, nanohemisphere on the substrate structure. If so, that's calculation. The peak was split into two, and the shorter one has reached to the 150 nanometer. That shorter wavelength is maybe the shortest record in the world for the surface parallel resonance. And that's a calculation, and that's one is the experiment. And also, we can obtain the split into two. But unfortunately, our equipment is difficult to measure the shorter than the 200 nanometer wavelength region. But you can see that begin to separate into two, and maybe another peak must be there. Right? That's why, now we found some analysis group can measure the shorter wavelength resonance. Then, I believe we can show that we can obtain the 150 nanometer resonance peak. That's the shortest record for the surface resonance. Okay, then we use this structure to enhance the UV light emitter. But one problem is so aluminum is very difficult to form the hemisphere structure because the wettability is very high. That's why the structure is not so beautiful. But on the other hand, gold is It's very beautiful. By using gold, very beautiful hemisphere was formed. That's why we combined the two types of the metal, gold for the nanoparticle and aluminum for the substrate. Then we use that's two types of the metal. Then that's a resonance peak, and we found the two resonance peak. And this red light peak is that's due to the gold nanoparticle, but still it has a deep UV light region. It has another peak. It's a combination mode of the gold nanoparticle and also the aluminum substrate. Then we put the zinc oxide light emitter on that structure. Then we can obtain the 47-fold enhancement. Huge enhancement is available. That's why this method is very good also for the UV light region. And but this structure is difficult to treat because the light emitter must be put on the metal nanoparticle. But in many cases, the emission material is there, and we have to put the metal structure on the light emitting material. That's why then we measure the temperature dependence measurement to optimize the internal quantum efficiency of emission, and that's 20%. It's almost similar to the epithelial growth quantum wave structure. Then we believe that we can fabricate the plasmon enhanced oxide semiconductor LEDs. That might be very easily and inexpensively fabricated using the sputtering and evaporation. We don't have to use the crystal epithelial growth techniques. That's why it's very cheap process. Obtain that kind of LEDs. And also that structure is little difficult to use. That's why first we prepare the light emitting material. Then we want to put on the structure on the light emitting material. Then first we deposit the zinc oxide. Then we fabricate the gold nanoparticle and the spacer and also aluminum there. Then still by using this structure also we obtain the huge enhancement. And the important thing is after that we have to one more time we have to annealing heat treatment is necessary, and we increase the temperature and around 500 degrees C heat treatment. We can obtain the 250 times the enhancement. That's very huge enhancement. So this structure is we just put this structure on the light emitting material. That's why it should be useful for any other material. So for example, aluminum gallium nitride, nitride semiconductor material, or some other material. So that's another result. And also this structure is very sensitive for the surrounding condition, and that's why it's good for the sensors. And finally, we want to use that as the antigen antibody sensor, but it must be good for the reflective index sensor. So first, I just deposit the silicon dioxide 20 nanometer. That's very, very thin. That's why by naked eyes, you can see the distinction. But we deposit the silicon dioxide on the silver nanoparticle on the glass. The color is a little changed. But we put that silver substrate and the nanoparticle structure. The color is dramatically changed. The color is vivid, shocking pink color and changed to the sky blue color. So it's very easily you can find you can sense the reflective index. Then next we just put the Huan serum albumin on that structure. It's some kind of protein. Then that's the result. By the naked eye, it's on the glass. That's the transparent. You can distinguish that. But on the metal nanoparticle on the glass, the color was not so changed. But this structure, similar to this color, initial color is very vivid, shocking pink. And if I drop the protein, the color is changed to the blue. So easily you can distinguish the color change. That's why this material is good for the colorimetric biosensors. Okay. And also we fabricate the grating structure, metal nanoparticle grating structure to obtain the wavelength dependence diffractive grating. So usually diffractive grating is not a wavelength dependence, but if you fabricate the structure, so we use the gallium and the silver and the gold for each wavelength region. And the property of the metal is different, and the gallium case size is a little small. That's a histogram diameter is 15 nanometer, and another one is almost 100 nanometer. But we fabricate that for the grating structure. And then that's the resonance peak transmission spectra. And that's why the whole structure, that's why it's grating structure. For grating structure, the metal particle area become half. That's why the resonance peak become half. But gallium case, it's a deep UV light region, and silver case, that's a green light region, and the gold case, that's red light region. For each wavelength, we can obtain the resonance peak, and that's why is a diffraction spectra. And that black one is a normal silver film grating. In that case, gold has a for UV light region, gold has no reflection, but another visible light region, almost that's flat. But using this nanoparticle, so it has some diffraction peak. That's why just only this wavelength light was diffract, and another peak was not diffract. And we can achieve the wavelength-dependent diffraction grating. Then we check that for the diffraction by the 3 types of laser beam: green laser, and red laser, and IR light laser. And for the green laser, for the normal metal grating and also the metal particle grating, diffract light. But the IR light for the normal metal grating, it's also diffract. But the metal nanoparticle light, it's no diffraction. That's why it's a wavelength dependence of the diffraction light. Then we use that for the third order nonlinear laser spectroscopy. So because nonlinear laser spectroscopy is it's also called the 4-wave mixing, and 3-wave can make the fourth another light. That's a nonlinear spectroscopy. And first 2 pomp beam make the interference pattern, and the third beam was diffract, and that's the fourth diffraction beam was generated. And by this method, you can observe the refractive index change. That's why no light absorption, light emission, just the refractive index has changed. You can detect by this method. And the good thing is the refractive index is very sensitive for the many processes, for the many time scales. For example, femtosecond region, the electron polarization, the electron transfer, the refractive index was little changed. And the microsecond region, the thermodynamics or molecular dynamics, the refractive index is changed. And the second region, the clustering or nanoparticle formation, the refractive index is changed. Then, but usually that alignment is very difficult. 3 beam must be the coherent, and also to enhance the light, that 3 beam also coherent. That's very complicated. But using the fabricated metal nanograting, just only 1 beam, you can obtain the special distribution of the light. That's why just easy. Just the 2 beam is good enough to form this same formation. So optical alignment become very simple. But problem is the signal beam and also the diffraction beam from this structure was at the same direction, the same color. That's why it has a large background, and the SN ratio is very low. But if we can fabricate the wavelength dependence grating, if so, PONF beam was deflected, but the probe beam was not reflected. In that conformation, we can obtain the low background, and we can improve the SN ratio and high sensitivity and high selectivity. Then we try to form the spectroscopy using the near laser for the excitation beam and helium laser for the probe beam. Then we try to detect the molecular dynamics of the methyl red in the ethanol. Then we just form this structure. And usually the nonlinear spectroscopy is very tuning, is very difficult. But just one time, just easily we can obtain the signal of the molecular dynamics. And that's why the free molecular dynamics in the solution. And that slow processes are probably the interaction of the metal nanoparticle and the molecule. Easily we can monitor the molecular dynamics by this method. That's another application. And before that, I use the random structure, but also I want to compare the regular structure. And by the regular structure, by using the E-beam lithography and the metal lift-off, we can fabricate the well-aligned, the same size and well-aligned that type of structure. But surprisingly, first we think that's the same size and well-aligned. That's why I think the resonance peak is very sharp and very strong, but it's not sharp and it's very broad. Then I add the heat temperature, heat treatment after the fabrication of the structure. If so, the resonance peak become stronger and blue shifted. That's why the after the heat treatment is necessary for that structure, we found that. Then we can reproduce that result by changing the metal parameter. Then we found that that metal dielectric function of the oscillation strength was increased with increasing the temperature, and also the damping factor become low. That meaning that by the heat treatment, metal crystal quality become higher. That's important. And also, that's extinction, and also that's a scattering image. And for the gold scattering spectroscopy, then gold case, at the temperature, the extinction was increased, and the scattering is much more increased. And the gold and the silver case, after the heat treatment, the peak was blue shifted, but intensity becomes smaller, but scattering become larger and also the smaller. Then that's why we found that metal crystal quality is much more sensitive for the not the extinction, for the scattering. And the scattering property is very important for the light enhancement. That's why that method is very important. I found that. Then now we try to use the nano imprint technology for the wide area fabrication, even if it takes a really long time. But using the nano imprint structure, we can fabricate a very wide area, very uniform structure like that. And we want to use that for the high resolution imaging like that. And we fabricate more good design. And maybe the cube array is much more better. Then now we try to fabricate the structure. And I'm sorry, time is almost, that's the last topic. And we can try the chiral controlling of the asymmetric metal nanostructure. So chiral property is very important for to distinguish the molecular enantiomer, but usually the signal is very low, very high stable detection is necessary. But recently, it became known that making the asymmetric metal nanostructure, this type of structure has a big, large circular dichromacy CD signal, and the interaction of that material and that molecule, very high sensitivity direction is available. Then we try to fabricate that asymmetric structure, and also we can enhance more using the metal nanosubstrate, right? Using the neon, similar to the neon structure. Then we believe that we can enhance much more CD spectra, and also, if the interaction is very strong, it should be useful for the topological controlling of the light. Then, but for the first, we start the simulation. But usually for the CD simulation, people are using the CW light for each wavelength. But if so, it should take a very long time. But we want to make the one pulse to the spectra at the same time. But for this pulse, it's not good enough. Then we think the many type of the function, and finally we found this function. This function is very good for the pulse circular polarization light. Then in this function, the phase shift is almost 90 degrees C for the wide wavelength region. And then for each wavelength, it's a very beautiful circular polarization is achieved. Then using that, and the first, that one is asymmetric, that's asymmetric, just a rectangle. In that case, almost left circular polarization and right circular polarization are almost the same, and there are no CD. Right? But if it's a parallelogram, it's a asymmetric structure. So the right circle, left circle, that the electrical distribution is different, and the extinction is different, and the CD was generated. Then that's why it's on the graph, and the CD is one peak, and the intensity is something like that. Then if we put that on the metal substrate, that increases 3 times larger, and also the peak is also 3 peaks of 10. That's why we found that using this structure, we can enhance the CD spectra. And another interesting is but it's a 4 symmetric structure, that's a shuriken structure. In this case, initial case, it has some CD, but on the mirror interaction, CD was completely gone. That's why we can control, we can enhance or reduce the CD by controlling this nanostructure. And that's a simulation, and we we fabricate this structure by the EV lithography, and we measure the CD for the transmitted and the reflected spectra. Then that is, but a polygonal structure is very difficult to fabricate. That's why we fabricate this type of structure. And that's on the simulation. And on the glass, one peak and 100, and on the metal, it's 3 times enhanced and also 2 peaks. And that's the experimental result. And the shape is not quite the same, but on the glass, only 1 peak, and on the metal, the peak has increased and the intensity also increased. Maybe the behaviors we can reproduce. Then, now we are thinking that by using this structure, we can control the circular polarization of the light. Then, if so, if we can strongly control the circular polarization, if we can put such type of the topological structure, if so, topological edge, in this edge, light can go to just only this direction, but not to this direction. If so, we can make the diode, like the light wave. And it must be very useful for the making the optical nanocircuit. Okay, and that's the last one. And I'm sorry, that time is that was 10 layer of the multiple quantum well, and the surface phase resonance is surface resonance. That's what I was saying. In this case, just only first layer was enhanced, but another one is difficult to enhance. That's why this method is not useful for such type of the multiple layer. But by experiment, we found that even such a structure, we can obtain more than 2 times enhancement. Then some theoretical analysis or something, we found that each layer was synchronized each other. Then that's why the lifetime was increased with increasing the layer number. And in this region, if it's synchronized each other, that's why even the surface plasma enhance the one layer. If so, at the same time, we can enhance the whole that layer like that. That's why this method is not only the first layer, but also the very wide area is available. That's why it's useful for the device application. And such kind of the phenomenon is similar to the super radiance or super fluorescence structure, and also partially fitted. Almost maybe the original is similar. That's why that recently we published a review paper of such kind of the super resonance and the ultra fast emission. Then, including the partial effect of metal and another structure. Then, if you're interested, please read this paper, Advanced Photonic Research Papers. Okay, sorry, I told that long time, but I would like to summarize the plastic metamaterial is useful even for the random structure, and the aligned structure is also okay. And also, that enhance the emission and also the resonance spectra and the tuned and for the very wide wavelength region, deep UV to the IR region, and it should be useful for the LED or solar cell energy devices and nano laser or imaging, high sensitivity imaging or sensing. And also we can control the chiral property of the plasmonic structure. Okay, then it should be useful for the photonic nanosecond structure. Then we can finally fabricate the photon computer using the wearable smart photonic devices. Okay, thank you very much for your attention. Sorry for the very rush talk, and also sorry for that. I take a little longer time. Yeah, that's it. Thank you very much.
Well, thank you very much.
Thank you.
Your nice talk. Oh, so the time to discussion. Do you have any comment or question or comment for audience? If no, so I'd like to some questions. So
Yeah, thank you.
about page 21 or something. So you
21.
said 17 nanometer is sharpest, I think.
21.
Yeah, yeah,
Ah,
yeah. This,
yeah, yeah.
why 17 nanometer is special?
Yeah, yeah, yeah. That's a very, very important point. So, because that's peak splitting is depend on this distance. Distance is close. The separation is become wider and wider. But that sharpness and the intensity is balance of the both electric field. That's why balance is good. If so, it's a more dark mode. If so, the quality factor is larger and it becomes sharp. But the balance is not so good. So it becomes bright mode. That's why maybe for this very sharp region is a very good balance for the metal nanoparticle electron mode and also the substrate mirror image mode. Yeah, I think so.
Thank you very much.
Hmm.
Okay, so is there any question or comment from audience? No, so I have another question. So your materials, all of your materials are very excellent. So I'd like to know, um, are these devices available in atmosphere, in air, or
Ah, yeah, that's
vacuum
also,
condition?
yeah, so depending on the material and aluminum case is aluminum is not so stable, but it makes the oxide layer, then it makes stable. But the silver case, the interface of the semiconductor and the silver is okay, but another side is yeah, silver is not so stable. That's also important. That's why sometimes silver and also the some protection layer is necessary. But for the light enhancement, the protection is it's also okay. That's a surface coupling is not there. But for the sensor, if protection layer is very thick, sensitivity become low. That's why for the sensor application, now you are thinking which thickness is best for the protection. Or yeah, or without the protection, just a metal condition is change or some alloy or something. If you can more stable metal, it should be okay. But yeah, that's very important point. Yeah, silver is not so stable. Gold is very stable. Gold case is okay. But surface plasmon resonance of gold is smaller than the silver. That's why we want to use the silver, but silver is a little difficult to treat. Yeah, that's a point. Okay,
Thank you very much.
thank you.
So, do you have any question or comment from audience? If no, so okay. So no, so uh, so thank you for nice
Thank you.
presentation,
Thank you.
presentation,
Thank
Professor Okamoto. Thank you very much.